Chapter 4. Technical Basics. Difference between common mode and differential mode. Common mode and differential mode refer to two different types of interference that can affect electronic circuits. Common mode. Interference. This occurs when the interference signal is common to both lines, conductors, in relation to a reference ground point, and often in the same direction. Common mode noise typically enters the system through radiation or conduction, and is often associated with electromagnetic fields coupling onto the lines. Differential mode. Interference. Differential mode noise or interference is the noise that appears between the lines, conductors, carrying the signal, and returns in opposite directions. It is often caused by the imperfect balance in a circuit or the layout of the PCB that allows the noise to be differentially driven. An example of common mode interference could be electromagnetic noise from a power line coupling onto a data communication cable, affecting both lines equally. Differential mode interference might occur in a twisted pair cable when the twist is not tight enough to cancel out the noise, causing a difference in noise level between the two wires. Causes and effects. Causes of common mode interference can include external sources like power lines, electrical equipment, or even lightning strikes that induce currents in the lines. Causes of differential mode interference often originate from within the electronic device itself, such as clock signals, switching power supplies, or other digital components. Effects of common mode interference can lead to disruptive behavior in high-impedance circuits, potentially causing data errors in communication systems or false triggers in sensor circuits. Effects of differential mode interference typically affect the intended signal in a circuit, leading to distorted audio signals in audio equipment or corrupted data in digital transmission lines. Measurement and analysis. Measuring and differentiating between common mode and differential mode interferences usually involve using a spectrum analyzer with a differential probe or a network analyzer. By measuring with reference to ground, common mode noise can be distinguished, while measuring the difference between lines can reveal differential mode noise. Identifying sources of interference often requires analyzing the system's layout, the geometry of the wiring, and the operational environment to identify where the noise is entering the system. Mitigation and solutions. Mitigating common mode and differential mode interferences can involve a variety of techniques and components. For common mode interference, solutions include common mode chokes or filters, which are designed to impede the flow of common mode noise while allowing the differential signal to pass through. Differential mode noise is often addressed using capacitors or differential mode inductors that filter out unwanted noise frequencies from the signal lines. Both types of interference can also be mitigated by improving the circuit design, such as using twisted pair cables for balanced signals, ensuring proper grounding, and minimizing loop areas that can pick up electromagnetic interference. EM field propagation and impedance in EMC. Basics of electromagnetic field propagation. Electromagnetic fields propagate as waves of electric and magnetic energy that move through space at the speed of light. These waves can travel through various mediums, including air, vacuum, and physical materials, which can affect their speed and behavior. In different environments, reflections, refractions, and absorptions can occur due to obstacles, conductive surfaces, and differing material properties, impacting how fields propagate. Impedance in EMC. Impedance plays a crucial role in EMC, representing the opposition a circuit presents to the flow of alternating current. It is a combination of resistance, real part, and reactance, imaginary part, which includes inductive and capacitive effects. Impedance matching is important in minimizing reflections and maximizing power transfer in a system. Mismatches can lead to standing waves, reduced signal strength, and increased emissions, which can cause EMC issues. Near field versus far field. The near field and far field refer to different regions around an antenna or an electromagnetic source. The near field is close to the source where the electric and magnetic fields do not radiate, but instead oscillate with distance, creating a complex electromagnetic environment. The far field is at a distance where the fields propagate as electromagnetic waves. For EMC, near-field conditions are important for understanding EMI at close proximities, while far-field conditions are relevant for radiated emissions and susceptibility at greater distances. Impedance measurement techniques. Impedance can be measured using various techniques and tools such as impedance analyzers, network analyzers, and LCR meters. These devices can provide detailed impedance characteristics over a range of frequencies. For EMC optimization, understanding the impedance profile of a circuit can inform decisions on filtering, shielding, and PCB layout to improve EMC performance. Practical examples. Real-world examples of the importance of field propagation and impedance in EMC include designing Wi-Fi routers that must operate effectively in the complex electromagnetic environment of a home, and ensuring that medical devices are immune to the various electromagnetic sources in a hospital. Case studies may explore how specific impedance matching techniques in high-speed data lines have successfully mitigated EMI, or how the careful placement of components within the near field of an antenna has reduced unwanted coupling. These examples highlight the practical applications and considerations of electromagnetic field propagation and impedance in achieving EMC. Wave characteristics in EMC. When we talk about electromagnetic disturbances, it's essential to understand that these disruptions don't just travel along the wires. They also spread as waves through the air between conductors. This wave-like behavior of electromagnetic fields means that interference can occur even when there's no direct electrical connection. One fascinating aspect of these waves is how return currents behave. Unlike direct currents which follow a single path, alternating currents, especially at higher frequencies, exhibit a frequency-dependent nature. As the frequency increases, these currents tend to follow the path of least impedance, which usually aligns closely with the outgoing current. It's almost as if the return currents are drawn to their originating currents, guided by the electromagnetic fields that are created by the currents themselves. This phenomenon has significant implications for how we design circuits, particularly when it comes to PCB layouts. To minimize the effects of electromagnetic interference, we must understand the paths that high-frequency signals will take and provide adequate return paths. This can involve careful routing of traces, maintaining appropriate spacing between conductive paths, and utilizing ground planes effectively. In practical terms, this means that designers must consider not only the physical connections, but also the invisible waves that accompany electrical currents. By doing so, we can create electronic systems that are more resistant to EMI, ensuring better performance and compliance with EMC standards. In conclusion, the wave characteristics of electromagnetic disturbances are a crucial consideration in the field of EMC. By designing with these principles in mind, we can mitigate unwanted interference and create electronic products that function harmoniously in their intended environments. Understanding crosstalk in EMC. Crosstalk is akin to a conversation in a crowded room where voices from different groups start to mingle. In electronic terms, it refers to a scenario where a signal from one circuit unintentionally affects another circuit nearby. This phenomenon can lead to a variety of problems, such as data errors in communication systems or unintended operation in control circuits. There are primarily two types of crosstalk: capacitive, which occurs due to electric field coupling, and inductive, which is a result of magnetic field coupling. There's also conductive crosstalk, which happens through shared power sources or ground paths. Crosstalk isn't just an annoyance, it can have serious implications. For instance, in high-speed digital circuits, crosstalk can cause significant data corruption, leading to system malfunctions. In audio equipment, it can manifest as noise that degrades sound quality. So how do we prevent crosstalk? Techniques include maintaining adequate spacing between conductors, using twisted pair wires to cancel out electromagnetic interference, and incorporating shielding where necessary. It's also crucial to consider crosstalk during the design phase, to minimize its effects through careful planning of circuit layout and cable management. In summary, crosstalk is a critical consideration in EMC, requiring a strategic approach to prevent and mitigate its effects. As electronic devices become more interconnected and operate at higher frequencies, understanding and managing crosstalk is more important than ever. Understanding shielding effectiveness in EMC. Shielding basics. Shielding in EMC is the practice of isolating electronic devices from their external environment to prevent electromagnetic interference, EMI. It works by either containing emissions from a device or protecting it from external electromagnetic fields. This is achieved using materials that either reflect or absorb electromagnetic radiation. Common shielding materials include metals like copper, aluminum, and steel, which are effective due to their conductive and, in some cases, magnetic properties. The choice of material depends on factors like desired shielding effectiveness, weight, and corrosion resistance. Measuring shielding effectiveness. Shielding effectiveness is typically measured in terms of how much electromagnetic energy is attenuated by the shield. Techniques for measuring this include using a shielded enclosure and measuring the electromagnetic field strength inside and outside the enclosure. Factors that influence shielding performance include material thickness. Thicker materials usually provide better shielding, material composition, and the frequency of the electromagnetic fields. Different materials have varying effectiveness at different frequencies. Design considerations. Incorporating effective shielding in product design involves considering not only the electromagnetic compatibility, but also factors like weight, cost, thermal management, and ease of manufacturing. The shield should be designed to cover sensitive parts of the circuitry without interfering with the device's functionality. This often requires a balance between achieving adequate EMC performance and meeting other design constraints such as size and aesthetics. Shielding in various environments. The requirements for shielding can vary significantly in different operational environments. In industrial settings, heavy-duty shielding may be required to protect against strong electromagnetic fields from machinery. In commercial electronics, shielding must often be lightweight and compact. In aerospace applications, materials must be robust yet lightweight, and they must withstand extreme environmental conditions. Each environment presents unique challenges for EMC shielding. Advanced shielding technologies. Emerging materials and technologies in EMC shielding are continuously being developed to address the evolving needs of complex electronic systems. Innovations include the use of advanced composites, conductive polymers, and nanomaterials, which offer improved performance, reduced weight, and greater flexibility. These new materials can provide effective shielding while meeting stringent design requirements for modern electronic devices. Advanced technologies are also being explored in the manufacturing of shielding materials, allowing for more customized and efficient shielding solutions. Understanding the Fourier transform. Fourier transform, simplifying the complexities of signals. The Fourier transform is a mathematical technique pivotal for understanding the behavior of waves and signals. It's like translating a book from one language to another, converting the time language of a signal into the frequency language. This transformation gives us the ability to see the individual musical notes, frequencies, that compose a symphony, signal. The Fourier transform is vital in EMC because it allows engineers to decompose complex electromagnetic signals into their frequency components, enabling the precise identification and mitigation of interference at specific frequencies within electronic systems. Why is Fourier transform indispensable? Imagine you're listening to a piece of music, and you want to understand which instruments are playing and when. The Fourier transform helps dissect these overlapping sounds into individual frequencies, revealing each instrument's contribution to the overall piece. In technical applications, this is crucial for several reasons. Engineers use it to detect hidden signals within noisy data, such as identifying a faint heartbeat in a medical EKG recording. In telecommunications, it's employed to encode and decode signals, so that a phone can send and receive voice or data over airwaves cluttered with various signals. For multimedia applications, such as JPEG images or MP3 audio files, Fourier transform helps in compressing data so that it takes up less space without significantly compromising quality. Applying Fourier transform, a step-by-step guide. Start with the signal. You'll have a signal that varies over time, perhaps a sound recording or a fluctuating stock market price. Transformation. Apply the Fourier transform, which mathematically breaks apart the signal into a spectrum of frequencies that make up the original signal. Analysis. Examine the resulting spectrum to identify which frequencies are present, and in what proportions, which tells you about the signal's makeup. Manipulation and reconstruction. If your goal is to alter the signal, maybe to filter out noise or to enhance certain aspects, you can modify these frequencies and then use the inverse Fourier transform to turn it back into a time domain signal.